So let's welcome the next speaker. So next speaker is Xinyi Zhang. Her talk is about NPC rethinking Dataplane through, let me check, through network-aware packet classification. Xinyi Zhang received her PhD degree in computer science and technology from Institute of Computing Technology, Chinese Academy of Sciences in 2022. She is currently an associate professor at the Computer Network Information Center at Chinese Academy of Sciences. Her research interests include internet architecture, software-defined networking, and internet measurement.
Okay,
so please.
Thank you for your introduction, and good afternoon, everyone. I'm Zhang Xinyi from Chinese Academy of Sciences, and today I'm glad to introduce our work entitled NPC, Rethinking Dataplane through Network-Aware Packet Classification. And the central idea of this work is to rethink how we design network dataplane by making it aware of traffic patterns. And let's start with the basics. Packet classification is a fundamental operations in the data plane. For each incoming packet, the packet classifier identifies the highest priority matching rule, which is defined by fields such as IP address, ports, and protocol. The matching results determines whether the packet is forwarded or dropped. And packet classification is widely used in software-defined switches, firewalls, and IDS. Its efficiency directly impacts the performance of the entire network. And packet classification has been studied for decades, and our work focuses on decision tree-based solutions designed for general-purpose processors. And the decision tree-based approaches include both cutting-based and splitting-based methods. And for cutting-based methods like high cuts, hypercuts, and IFI cuts, recursively divide the root space into equally sized segments. And splitting-based methods like hypersplits split each interval into two parts. And the existing algorithm mainly constructs data structures based on rule set features. But in real network, what truly matters is how many packets the classifier can process per second. And this is not only depend on the efficiency of the lookup structure, but also on how it interacts with the traffic distribution. However, current methods implicitly assume that each rule has an equal chance of being matched. And in real network, this assumption does not hold since the traffic distribution is highly skewed. And to illustrate this, we analyzed two open source data traffic traces. And for each data set, we collect UDP and TCP packets and record the number of packets for each flow. And we clearly observe that a small number of elephant flows dominate the traffic volume, while most flows, known as mice flows, contribute only a tiny fraction. And we use an example to show how traffic distribution affects lookup performance. And the left figure shows the geometric representation of the rule set. And taking high cuts as an example, the middle figure shows the field Y is chosen for the first cut. And in this case, packet matching rule 5 must check 3 levels to find a match. And however, if we take traffic distribution into account and cut the field X first, and as shown in the right figure, those same packets only need to reach the second level. And this observation is the foundation of our work, that is, classifier optimization should be guided not only by the characteristic of the rule set, but also by the traffic patterns. And in this work, we present NPC, a network-aware packet classification framework. And NPC first brings traffic mirroring and packet classification module together in a unified framework. And it includes 3 modules. The rule set analyzing module examines the characteristic of the rule set and choose the most suitable decision tree strategy to reduce memory overhead. And the traffic mirroring module collects real-time traffic statistics and identifies the top K flows using a sketch. And this information will be used to guide the construction of lookup structures in the packet classification module. And finally, the packet classification module handles the core Dataplane task. And it matches incoming packets using the traffic route-driven decision tree, or TRD tree in our work, which is designed based on traffic and route features. And additionally, the TRD tree is updated as the network state evolves. And now let me introduce each module in more detail. And in the route set analyzing module, we use two simple metrics to measure how much the route overlaps. And the first route overlap count measures the number of intersections between routes. And it reflects the degree of route duplication. And if this value is high, we use a multi-tree design to reduce memory redundancy. Otherwise, we choose a single tree construction. And for the single tree case, we introduce the second metric, which is the field overlap weight. And it measures the average number of overlaps within field intervals, indicating the density of overlaps. And when this value is high, we prefer splitting-based methods because they reduce route duplication. And when this value is low, the routes are sparse, and we choose cutting-based methods because they accelerate lookup speed. And after selecting the appropriate tree type, we proceed to construct the TRD tree. And the route features can be directly derived from the route sets. Traffic information needs to be collected in real time. So in our work, we use a sketch to monitor network traffic. And the sketch is a probabilistic data structure for summarizing high-volume streams with limited memory. And more specifically, we use a hash table along with a data structure called Traffic-Driven Stream Summary, or TDSS, to track flow frequencies. And unlike traditional methods, we do not care about the exact counts. And we only need the top K flows and a coarse-grained frequency estimate to guide the construction of the decision tree. And to achieve this, TDSS groups flows into frequency ranges. And this design reduces memory overhead and avoids costly dynamic memory allocation, which improves speed. And after collecting the traffic features, we introduce our TRD tree construction approach. And when building the tree, the first step is to choose which dimension to split or cut. And the traditional methods usually make this decision based on route set itself. But in TRD tree, we take both traffic and routes into account. And we use two key metrics. The first is a uniformity score. It shows how evenly traffic is distributed across the dimension. And the second is a weight score. It measures how heavily routes overlap in that dimension. And by combining these two metrics, we can choose a dimension that spreads traffic more evenly and avoids too much route duplication. And after selecting the dimension, the next step is to partition the route space. And there are also two common ways. Splitting divides a dimension into two parts, while cutting divides it into multiple equal-sized segments. And carrying methods usually decide where to split and how many cuts to make based on route features. But in TRD tree, we also take the traffic pattern into account. And for splitting, we balance lookup efficiency and the storage overhead by minimizing the deviation between the traffic volume and route weight. And for cutting, we apply more cuts to high traffic nodes to reduce memory accesses, and fewer cuts to traffic nodes to save memory. And we also design traffic-driven leaf thresholds. In sparse regions, we use larger thresholds to reduce leaf nodes and save memory. And in dense regions, we apply smaller thresholds to reduce memory accesses and speed up the lookup. And in real networks, both the route set and the traffic can change over time. And to keep up with these updates, NPC continuously monitors changes in routes and top K flows and uses an A/B switching strategy for classifier structure updates. And because NPC is traffic aware, it also needs to resist malicious traffic. And to defend against burst-induced top K replacements, such as DDoS attack, NPC checks whether new flows persist across multiple time windows. And in addition, to detect traffic distribution flattening, NPC uses Gini coefficient to measure the skewness of the traffic. And with these checks in place, NPC remains stable and reliable, even when the network is highly dynamic or under attack. And our experimental setup is shown in the slide, and we compare NPC against 5 baseline algorithms. And for dataset, we use both IPv4 and IPv6 from ClassBench and ClassBench-NG. And in the evaluation, we focus on key metrics such as memory access, memory footprint, and construction time, as well as system-level features like the attack-aware update performance and the integration of NPC into open-way switch. And under this setup, let's start by looking at the most basic metric: how fast can NPC classify packets? And as shown in the figures, traffic-driven design significantly improves lookup performance. And for IPv4 rule sets, NPC achieves a speedup ranging from about 1.9 times up to nearly 24 times over the baselines. And for IPv6 rule sets, the gains are smaller but still meaningful, ranging from about 1 to 4 times. And in terms of the memory overhead, NPC continuously reduces memory usage by optimizing rule partitioning based on overlap analysis. And compared with other methods, it achieves a better balance between memory consumption and lookup performance. And in the face of dynamically changing networks, NPC can rebuild its structure within 10 seconds. And even when traffic patterns shift significantly, its performance still stays stable. And our evaluation also shows that NPC is able to resist against malicious traffic. And for distribution flattening, when low-frequency flows flatten traffic, Gini-based monitoring can detect attack. And for top K replacement bursts, when high-volume flows trigger shifts, the attack-aware mechanism prevents data structure rebuilding. And we also compare our TDSS sketch with Heavy Keeper and Cuckoo Counter. And the TDSS achieves high throughput while keeping low memory overhead. And since our focus is not on exact flow sizes, a small sacrifice in accuracy does not hurt performance. And as the evaluation shows, TDSS guided data structure significantly reduced memory accesses compared to the baseline algorithm. And finally, we integrate NPC into open-way switch by adding the NPC cache between the EMC cache and the Megaflow cache. And compared to the native system, the throughput improvement is more than 10 times. And to conclude, our study rethinks packet classification from a network-aware perspective. And we design NPC, and it combines the sketch-based traffic monitoring with packet classification. It leverages both traffic characteristic and rule set features to guide tree construction, enabling efficient packet classification. And we believe this approach emphasizes the value of combining measurement with classification for an overall design and opens new directions for intelligent data plane algorithm. And thank you for your attention. I'd be happy to answer any questions.
Thank you, Xinyi. Any questions from the audience? Okay, maybe I should field one question. So I think on one of your slides, you mentioned that the IPv4, comparing the IPv4 and IPv6 speed up. It seems that IPv6 speed up is significantly less than IPv4. Do you have any insights of why that is the case?
I think that, this is because the data set we use, because the IPv6 we use is a smaller data set, and that is not, that is highly related to the characteristic of the rule set. So maybe there is a difference between the improvement of different data sets.
Okay, thank you. Any question from the audience? There's one.
Hi, thanks, nice talk. Just a quick follow-up on that. So for the data set used in the evaluation, where does the traffic come from exactly? Is it synthetic or is it real-world captured traces? Or?
No, the traffic we use is derived from the rule data set. And like the ClassBench it also has a tool to generate traffic based on the rule set, and we can use different parameters to change the locality of the traffic based on the rule set. So the traffic we use in our evaluation is also from the data set we use.
Okay, thank you.
Okay, thank you.
Okay, any other questions? Okay, let's thank Xinyi again. Thank you. Great talk.